Okay, should we go? Okay, so I guess you pretty much more or less know who Brendan is, principal developer of Skyline. So we're going to be learning a lot about Skyline this week, and Brendan is going to give an introduction. And I think it's fair to say he's like the only person who travels to all of these courses that I mentioned that happen around the world. So he seems to just spend his days running around getting on planes, promoting Skyline. But it's to our benefit. So Brendan, please.
All right, so hi, yeah, I'm Brendan. I hope it's, I view it as more as promoting targeted proteomics and teaching people to do targeted proteomics. And yeah, I got started on this project very early, and you know, at its inception, I wrote the first line of code for Skyline, which is the first time. I had already been doing software for 15 years, and it was the first time I'd ever started a project from scratch, and so that was really exciting. But yeah, it wasn't long before I had been working in proteomics, and I was really excited. We had a very engaged set of users in the CPTAC program that was National Cancer Institute in the U.S. But then I all of a sudden went, wow, this is a really small market. And I was like, we're one of the leading targeted proteomics labs, and we have one triple quadruple instrument in our lab, and most of the people are the same. So part of growing, you know, what we can do with targeted proteomics was moving into these other areas. You can see that, you know, Skyline started. If you came this morning, you've seen this chromatography-based quantification. Skyline definitely started with SRM, as did the Aebrosol lab. We were sort of all on the same journey, and I've been coming here for, I think, 7 years. It's been fantastic. I really love this group, and I always go home with like, oh my gosh, I have all these ideas. And then, you know, we moved into PRM, and we had done a little bit of the DIA analysis, but then, you know, the Aebrosol lab showed up at ASMS with SWATH, and we're like, oh, well, they're doing the same thing too. And then also just because the mass spec community has done this for like 20 years, extracting chromatograms from MS1, and you know, MaxQuant is probably the most popular example of this right now, but there's also Mascot Distiller and stuff. But this is something that we've done for a long time, but we adapted Skyline to do that as well. And so then Skyline can now do all 4 of these methods, and I break them up like this, where we've talked about, I think, targeted acquisition versus what I called survey acquisition. And targeted acquisition, you have to tell the instrument before you're going to collect anything what you're going to collect, and so that was a really important way of looking at Skyline. Was okay, like the instrument just understands a bunch of numbers, and to actually measure anything, you got to tell the instrument a lot about these numbers. And so, yeah, when I arrived, Mike said, well, first we'll do a little thing that helps us set up the instrument, and then we'll go do a data analysis tool. And I was like, that sounds like one thing to me. And that's where Skyline came from. And so then this is just a schematic. There are going to be lots of graphs in this, and I'm actually not going to talk the whole time and ask you guys some questions. And so try to orient yourself and understand these graphs. I know it's really hard when I always feel kind of depressed when I watch other people's presentations, because like the graphs go by and I'm like, I didn't understand that graph. But anyway, this is just the typical 3-dimensional space that we always measure with mass spectrometers, whether we're doing MS, you know, fragmentation, or we're doing MS1. And then Skyline allows you to take these slices out of retention time at various mass to charge ratios and then presents it like this. And then we use the area under this curve as a proxy for a quantity, a peptide quantity. So hopefully everybody knows that. Here's a graph. Here's an easy graph. So yeah, this is something that I presented to NCI in 2010 after I guess you can see almost 2 years of developing Skyline, and I was super proud. And I said, man, look, it was started 1,000 times in a week. And so this is showing the releases that I'd done, and I actually, it didn't get back up to 1,000 for a while, and I felt really guilty. I was like, oh, did I overstate that? But yeah, so here you can see the releases. Can anybody guess a question that was asked to me from the NCI? I've been at it 2 years. When are you going to release a 1.0? And I was like, oh, well. But so coming at Microsoft, we used to say version numbering is a marketing decision. And so, yeah, I had decided I'm not going to get expectations too high. I'm just going to keep releasing. So here we are now. Actually, I've lost the version numbers, but I'll show you them in the next thing. This actually doesn't even, you'll see, doesn't even go out to 2015. But this is the growth of Skyline. We're almost done with our 9th year of development. That's going to end in August. 6 developers now focused on it, over 500,000 lines of code. It's all open source and free, and that's sort of who we are. We're not going to change that. We're trying really hard not to change that. And 60,000 lines of code for testing. We're very, very into testing and having testing rigor and making sure that every release is as reliable as the last one, and people don't go like, ooh, don't touch that new release. You really broke things. And so actually you can see at the top here, this blue at the top is what we call the Skyline Daily Release. And if you don't have the Skyline Daily Release, you've never used the Skyline Daily Release, I encourage you to download it. You can use both side by side. You have to be a little bit conscious that sometimes the Skyline Daily Release, if you save a document with the Skyline Daily Release, you may not be able to open it with an older release. But we've seen a lot of people picking up the Skyline Daily Release, which we also take as a good complement to the level of stability that we're able to maintain with all these tests that we have and run so frequently. 8,500 registered users, 8,000 instances started each week, more or less, and over 1,000 citations. And then the funding appears to be pretty solid. We've gone through several cycles, and now all 6 instrument vendors have contracts and are renewing them yearly, and we have a fairly stable NIH funding. This is up to the minute. I did this like last night. You just can start to see 3.7 eking out here. Hard to say why we don't have as big spikes as we used to. Maybe, I think we have slower turnover, so we definitely saw, within a few days when we made a new release, everybody would just like hop on that new release. But yeah, maybe we're also sort of leveling out here. And then I also like to say that if I've learned anything quantitative in 9 years, it's that not a lot of targeted proteomics gets done between Christmas and New Year's. So if you can read that graph, you understand that. There's actually dips in August too. I mean, there's a lot of interesting information you can get here, and I definitely look at these new releases. I look very carefully at like how quickly are people taking them up, because again, that's like tells me if people really care about what we've done recently, or whether they're just happy with what they had before, or they're afraid of what we just released. So then this is a plot that I did for Mike maybe 2 years ago, when he said, "Oh, he saw one of these plots and he says, oh, it seems like people aren't upgrading as quickly." And I went, well, okay, this is the upgrade plot. And so from 1.1 onward, you can see sort of within 7 days, how deep do we go? And so it used to be that within 7 days, we were rarely below 65% of our users. So we were rarely below 35% of our users that hadn't upgraded. And so you can see that, just as I was saying, we're going deeper now. People within 7 days we're at 50%, but we're still getting up pretty, up above 90%. And you can see that we have a lot of people using Skyline Daily, which we're really happy about. This is a map of our website accesses, and this big thing, that's Seattle. So we access our own website quite a lot, I guess. And then these are by country, the top countries accessing the website over the last 6 months. Obviously, there's quite a lot of activity in the U.S. It sort of dominates, but it's always been exciting to watch Europe grow. And we're, India, we've been to a couple of times. I did a course with Ben there. I was just in South Africa last year. And, the Far East and Australia are exciting to us too. So, yeah, and this is zooming into Europe. It used to be, much more like, I'm kind of amazed at how, like there's this whole place here that's just covered. And that big blue thing here, that's Zurich. And it also sort of dominates always, because yeah, we've always been working very closely with people in Zurich. And you can look at other places, and I actually had to look up, where is Paisley? It's in Scotland. So yeah, that was pretty exciting. And yes, a lot of teaching of targeted proteomics, and you know, it's been great to teach with the people at the ETH. They started this whole course. I just telling somebody, I attended twice before I had the courage to organize our own course at the UW, and it really very much shaped how we did that. And then we've been growing them, and we're trying to add new instructors. And so if you end up feeling like, hey, I'm an expert in Skyline, well, you know, international travel could be in store for you if you contact us. So here we are at Zurich, and we still have Seattle and Barcelona and Dublin left for this year. There's quite a lot of documentation for Skyline. So, you know, your education doesn't have to and shouldn't end here. There are all these tutorials to work through. We've been doing a webinar series. We encourage you to attend those live, but also go back into the archive, because they're all recorded, and they're all organized to be done sort of like the SkyJam hands-on session you did this morning, where you could sit. You know, we provide all the data. You can download it, and you should be able to go through step by step. And I've been told that, like, oh, having it on video, you know, in a SkyJam in the morning, you can't tell me to pause, but you know, when you're watching me on video, you can. So I encourage you to look at those and do those. And then we've 9 out of 14 of the tutorials we've translated into Japanese and Chinese, and that was a major effort. Oh, these are all the webinars we've been doing. So this is, we were writing a paper for the MS1 extraction paper, and we're trying to, and you know, we got some review feedback of, or maybe we were just talking among ourselves, like, well, what's so unique about this? People have been doing MS1 extraction forever, and I said, oh, you know, I think, you know, we're optimizing, you know, or we're reducing the time to understanding. You know, so time to human understanding is a bottleneck in this field, and what we're doing is reducing time to understanding. And then lately I've been reading Daniel Kahneman, who's a cognitive psychologist, and he had this thing called Wisiati, which is what you see is all there is, and that's actually cognitively the way the human mind works, is that we will take what we know and create a plausible story for it, and frequently completely unable to imagine what we don't know. That's the way the human mind works. And so I decided, well, that's, you know, what you see is what you believe. And then this is really my belief is like, hey, see, you know, actually dig in, see more, and that's what Skyline's really great about. And so even if you use whatever tool you use, this is still an incredibly useful data debugging tool. And you should for that alone, you should gain mastery of it, and yeah, and that, you know, that's what gets me the most excited about what I do, is trying to figure out, like, well, how, you know, when I learn something about the data, how can I make that obvious to everybody? You know, how can I, oh, that plot that's really useful, let me integrate that into Skyline. And so, yeah, if you look at the Skyline implementation of mProfit, you know, we took all the plots that they put in the paper and said, let's just make those available to everybody, you know, the plots that are in the paper, and we make them sort of interactive, and so that's what we do. And so I would say that, you know, if you just expect your tool to spit out a bunch of numbers, which are, you know, intensities for your peptides, or quantities for your peptides, you're at what I think of as the satellite view, and this is what you might be seeing. And I mean, you can certainly learn stuff from here. You can run statistics on this, and you know, and this is, and here we can say, wow, there's a lot of people using center pivot irrigation. And then this is the proteomics version of what I consider the satellite view. You got samples across the top, and then sort of targeted query values this way, and then you get some measure of quantity. But actually, there's a lot going on underneath these values, and I've seen a lot of mistakes, a lot of misunderstandings, a lot of a lot of issues that if you stopped here, you wouldn't notice, and you wouldn't And people do stop here, and I think that stopping here and sort of viewing the tool as just this set of steps that I have to go through and then I get this, that's the most likely reason you don't get over that mountain bioinformatics that Rudy showed on the first day. So now's the participatory part. I'm going to show you graphs, and we're going to look at the graphs and try to understand them together, and then volunteer early, because if people don't volunteer, I'll start calling on people. So as soon as you think you have some explanation for this graph, go ahead and let me know. So this is, what is this? We go out to 13 times 3 more or less, so about 40 replicates. This is retention time. This is a plot that just comes right out of Skyline. And when I saw it, I was like, whoa, what's going on there? So why was I surprised by this plot? Is anybody else surprised by this plot? Why? What? What? Yeah, wow, like the variance in retention time. Boy, what was going on with that chromatography, right? Anybody have a hypothesis?
This is the logical order, but not the order in
Oh, yeah, the answer's right down here. Right, it's the logical order. I didn't know anything about this data. Somebody gave me this data, and I imported it into Skyline. This is what I saw. And I didn't have a little label saying it was the logical order. I just went like, wow, I was like, what's going on here? This is the worst retention time stability I've ever seen. And then I went into debugger and figured it out. And then I went like, okay, I'm going to make it possible for anybody to figure this out in Skyline. And so what we did was we added a feature. You can right-click on this plot and say, I want this ordered by acquired time. Because we read the acquired time. And at that point, actually, we weren't reading the acquired times. But we read the acquired times of all the files. And when we sort by acquired time, it looks like that. And then it's like, oh, well, that makes total sense. And so there's some drift here. And, it's moving. But I would say, in general, this is not surprising to me as long as these things kind of overlap. But, it's like, yes, I would really rather see it go straight across. But that we can get by doing alignment, yay, and there it is, aligned. So yeah, that's not IRT alignment. That's alignment. This is DDA data, and we just aligned by the ID. So the alignment has been around for a really long time. IRT is newer, but we just did normal alignment here. Okay, so and this is actually labeled too. So this is again retention time a bit. This is like 80 samples. This comes from the Eberswald lab. It was collected by Ruth Huttenhain in a breast cancer study, and this is one of the peptides. And well, I guess unfortunately it's already labeled. So what happened? I've labeled it with 2. So these were actually collected, a month apart. But again, I was just faced with like, whoa, why? This is. I know that this is ordered by acquired time. Why is there that big jump? And this is where I say, oh, we're going to make it possible for everybody to get that. Not only can you order by acquired time, there are these grids. This is the results grid. There's a document grid, and hopefully I'm going to get into showing you how to use these, where you can actually look at the acquired time, and then that's where you can see, oh, look, it goes from 2022 to 316, and who knows what happened to the instrument in that time. Okay, so and this is actually aligned by IRT. That's what it looks like. So this gives you the like, wow, if I align, then I get rid of that. Even though I collected them a month apart, you can see a little bit of something there, but you really wouldn't draw your attention at all. Okay, well, we still have the dates here, but so tell me about what you see here and what's unusual. Like, what's going on in these two plots? We got 2 peptides collected in the same experiment. This is an SRM experiment. We got light and heavy, and yeah, what's happening in the first one? Who can tell me what's happening in the first one? This is an easy question, so answer quickly. What? Yeah, and which way is it changing? Up. Yeah, so who knows what, like, oh wow, this thing just like all of a sudden is so like, so what's the hypothesis? Why would this thing be going up like that? Anybody? Clean the machine. Yeah, that was my idea too. Oh, they clean the machine. Okay. So what's going on in the second plot? Goes down. Yeah. Hey, you guys are getting the idea. Okay. So so what's your explanation for that? Why did it go down? What? Platform degradation after cleaning the machine. I mean, these are like these are in the same run, right? So I don't know either, but yeah, I've labeled a global normalization problem. So if we're using a global normalizer, right? So these are heavy light pairs, so that's kind of nice. But if we were using something like, you know, total ion current or anything that's global, it's going to have the wrong effect on one of these, right? So peptides are unique, they behave uniquely, and I would say that this is a really extreme example. Most of the peptides in this sample were doing this, going up a little bit, and I chose probably the most extreme one I could find. And then 5 to 10% were going down like this. You know, so it was, to me, it was like, whoa, I guess you can't really, you know, you can't rely on global normalization for all of these peptides. But of course we do, right? So statistically, still 5 to 10%, you know, okay, well, we're going the wrong direction, we normalize incorrectly, but overall we're winning, so. And this is if we, since actually we had injected reference standards, when I take ratios and normalize, then wow, that, you know, again, just like IRT normalization, goes away. Looks like, you know, totally constant. So are either of these biomarkers? Wow, that was an easy question. No, like there's like no variance across all of these. I mean, some of the, I mean, I guess if you were to go, well, maybe these are all diseased, but no, it wasn't. Okay, so new plot inside Skyline. This is actually DIA data, Hufnagel QE DIA targeted. So we had a set of things, and I came across this one. This is actually looking at the precursors, not the product ions. So as we've said, you can extract the precursors and the product ions when you do DIA. And at this point, I'm looking at the precursors. Who can tell me what's going on over here? What's this? Hypothesis. So is everybody oriented? Do you get this the graph? This is so these are the precursor chromatograms. So we got isotopes. We got the monoisotopic peak is blue, and then the M+1, and then the M+2, and then here this is the actual spectrum it was extracted out of, because in Skyline we can click on the chromatogram and it will pop up the spectrum, and you can see these are the you know, this is profile data, and this is the extraction range that Skyline's extracting, and it looks pretty good, right? But what is this? Chromatography, yeah, so it might be tailing, right? Or any other guesses? An interference, that's a good guess. What else? Overloaded columns, or yeah, like a friend of mine told me that, you know, sometimes, so I would go, oh, is there a proline? Is it a doubly eluting peptide? You know, sometimes you see things come up and down. This might just all be the same thing. And so, yeah, so we've basically heard an interference, or that's really part of the same peptide, right? Those are our two choices. It's not part of the same peptide, or it's part of the same peptide. And so with Skyline, you know, again, we're always like, oh, how do we help people answer those questions as quickly as possible? Well, you just click on that point, and now you can see the spectrum from which this was extracted from, and what is it? Interference, right? And why? And somebody explained to me why they know it's an interference. What? Yeah, it's kind of shifted a little bit to the left, so it's not. There's a higher mass error out here. So if we were to select this, Skyline, right here we've got 2 ppm mass error, and if we were to select this, probably Skyline would go like 15 ppm mass error. What else? Yeah, so it's actually a peptide that is heavier or lighter? Lighter, so yeah, so this is its monoisotopic peak, and we're actually extracting M+2 and M+3 and M+4. So okay, yeah, so that's one of our lab mates described this particular view and graph as like taking the blinders off. Just being able to click on something and see the spectrum from which it was extracted can be incredibly useful at times. Okay, so this is just to orient you to a set of graphs. This is anybody who came to the, most of you came to the, or a lot of you came to the morning session. We saw this graph before. So this is the whole Skyline UI. You've seen the retention time graphs. You've seen the peak area graphs. And those are these 2 summary graphs. You can see, who can tell me what kind of experiment this was? DDA, yeah. So, and this is the, this is actually very similar to the graph. This is the chromatography we saw in that first thing. So we're now, we're ordered by acquired time. But what does the peak area graph tell us about what the kind of experiment this was? A time curve or a... Yeah, dilution curve, right? So it's a dilution curve experiment. If this is ordered in acquired time, how did that person choose to do this dilution curve? And they did it in 3 cycles. So when we joined CPTAC, they were doing their dilution series as like 1, 2, 3, 1, 2, 3, 1, 2, 3. And so they would do a single cycle, and Mike was the one who's like, that's not the way to do it. You don't really get a realistic understanding of your variance that way because you just collect everything. So if you're saying, wow, I got a CV of 5%, you're underestimating your true CV. So and there are actually washes in here that we don't have. But so this is, I guess according to Mike, a more rigorous way to do a calibration curve. So we have DDA data. Again, these are all precursors, and we have IDs here showing us where we had spectrum matches of MS-MS spectra, but this is DDA data, so we can't actually extract chromatograms out of this. This red one shows you this spectrum. There it is close up. Okay, so that's just to orient you. This is a data set, or this is a graph from a data set where the experiment was yeast background. 6 proteins were injected at various levels, and then this was an ABRF SPRG study, an informatics PRG, which is Proteomics Research Group. Informatics, Proteomics Research Groups. They set up this experiment, and then they sent it out to people and said, tell us what's changing. Tell us the proteins that are changing in here. And so what I did was I took all that data and I went, okay, let me look at what peptides are statistically changing, irregardless of the proteins. Let's just look at the peptides. And I found peptides that really there shouldn't be any way they could be changing, because this peptide, although I don't label what peptide it is, it's not part of one of the proteins. So it's part of the yeast background, which wasn't changing. And so when you look at this, immediately what draws your eye is, what's the hypothesis of what could be going on here? Isotopic, like, wow, these are 0.9s, those are great matches. The I.P, talked about the dot P as a correlation score that matches, that tells us how well we're matching to the expected isotope distribution. And these guys are at 0.5. And I would say that where the library.p that Ludovic presented is, a 0.8 for a library.p is kind of okay. You should expect like 0.9 and above. I guess this is 0.89. But the isotope distribution .p's should be very, very good, and this is not very good. So we can guess, even before we look at the chromatograms, something's wrong. This is probably some weird interference. But again, if I didn't even come down to this level, I could just take these, quantitatively, statistically, wow, that's a beautiful change, right? If you just looked at these as bars and you didn't see the dot P's and all the other information that Skyline's giving you, this would be a statistically significant change. And so then here it is, here's our thing. And so Skyline shows you these blue stripes are aligned ID times. So who can tell me? So it's this 3x3 9 samples. They're ordered the same way as in this plot. Who can tell me where, how many of these runs did we identify this peptide in? Anybody else? I count 5. Where's the 6th? I get 3 here and 2 here. So it wasn't, that really is the same thing. We can tell by the alignment, but the way we're choosing this peak is based on the alignment of these ID times, and it's also the way we're choosing this peak. But here, it's really not the same thing, right? So okay, we should delete that one and forget about it. Okay, how about this one? Anybody, is it changing? Yeah, no, yeah, okay. Can anybody see anything that they think is like, yeah, what? I can already tell that it's not gonna. Did anybody have a hypothesis of why? This is in a protein. It's a single peptide for a protein, and we know the protein can't be changing. It's just a normal background protein. So anybody have a hypothesis as to why this is happening? So now you see, what you see is what you believe. You can't actually maybe come up with a hypothesis until you see more. So Skyline makes it easier for you to see more. What do people see now? What? Oh yeah, high mass error, look at that. 20 and 3 and 3. What else do you see? Well, what do you see up in this top row? What? So you can see this peak that we're picking. We get an ID in it most of the time. Actually, in all 3 runs, we get an ID. We're actually getting IDs down here. We get IDs in every run, right? But what do we see up here? Yeah, there's an interference. There are 2 peaks here. And so this is what I call, and actually you can see that it's 20 ppm. Ooh, the plot thickens. So I like to talk about this like interference, like why we would love to have no interference at all. When the interference doesn't coalute with our peak, it actually offers us more information, right? I call it the interference landscape. So if I had an isotope labeled reference peptide, then I would have this beautiful curve, and I'd go, if my peptide went away completely and there was nothing under it, I would say, here's evidence that my peptide went away completely. But when I was in South Africa, just in December, somebody offered a beautiful example of this interference landscape that I had taught her in Barcelona, and there were 2 peaks. There were basically 3 peaks, and she did a knockdown experiment and said, voila, you can see that that peptide is gone because the 2 peaks stayed and there was nothing in the middle, right? So the interference landscape can give you reference points, and especially if you're doing manual integration and this just sort of went to nothing, you would go, oh, well, I still know where it is. But it's really easy to zoom in with Skyline, and so the next thing we might do is zoom in to this one to try to understand like what's going on. And actually these are all now, there's a very easy thing that actually was inspired by Tina Ludwig, we do synchronized zooming in Skyline. So this is all at 30 million ions per second of intensity. And now when we get down to this level, you can see this little thing. But I mean, who can blame a tool for not catching that shoulder as a separate peak? No tool is going to catch that, but the ability to see it will allow you to make sense of it. Okay, so cautionary tail, I was involved in it. Before that IPRG study I just presented, I was involved in another PRG study. These PRG studies are great. And these are the results plotted. You know, a bunch of people use Skyline, and then I found that there were some issues with getting data into Skyline. And you know, if you were very attentive and careful, you could get things in correctly. And we've tried to make it easier and more like we call out the problems. But it was very easy to get your data into Skyline and then just send in your results. And some people did that. And so, okay, well, so hypothesis time. Well, actually, over here, we have everybody color-coded by the number of IDs or manual. So that meant like if you manually integrated stuff, we would count that as the same as having an ID. And so that's, you know, just to again, the number of IDs is, you know, how many of the peaks actually had an ID in them. Okay, and so then here we go. We have 80 to 100 and 0 to 20. And so okay, what can you tell me about this plot? Oh, so sorry. These numbers are correlation. So basically we took sort of the winning idea of retention time and said, how well does this run, or does this set of samples correlate to the winning idea? And then we also took the winning idea of the log2 peak area, and we said, what's the correlation for that? And so this is correlation of 1, this is a correlation of 0.9, and this is 0 correlation. So who can explain what we see in this graph? Where are all the people who had no IDs, basically? 0 to 20% meant they had very few IDs and very little attempt to do any manual integration. They're all here with really terrible correlation to the right thing. So these are people that I would say try to use Skyline as a protocol, set of steps, output, and they sent us the output. Without very much attention to detail, without ever looking at the kinds of diagnostics that I've just shown you, because if they'd even looked at one single plot like this, they would have noticed, well, wait, I don't have any ID annotations. You know, that's a problem. So, and then you know, then the people with, you know, 80 to 100% are all up here. So, you know, so basically what we got from that was the tools work really well when you know how to use them, and you know, and we then spent more time to try to improve and make it less likely that you would fall into a pitfall like this. But yeah, definitely people who just tried to go through the sets of steps, and this is the Mount Bioinformatics, where you could, you know, if you don't have enough attention to detail, you could turn in some pretty bad results. Okay, so this is a plot sent to me by Dario Amodei from the Mallick lab at Stanford when he was there. We had been working very hard to implement mProfit. So I said we've been working for a year to implement Trick, and we're still like validating it very carefully. At this point, maybe we've been working 6 months to a year on mProfit, and we got these, you know, we came up with this way of generating these ROC plots, and we were actually, tomorrow when I do our hands-on here, we're going to be focusing on some of these ROC plots. And this, you know, these two lines up here are open swath. This is the original Skyline scoring, which, what can you tell me about the original Skyline scoring from that blue line? There's actually 2 observations you can make. So are people familiar with an ROC curve? Yeah? And so is that a good ROC curve? No, it's a bad ROC curve. But so we tend to focus a lot, we focus on the ROC curve and how well it sort of hugs the y-axis. But there's actually a second point of interest here, which, yeah, boy, so the original Skyline score was poorly calibrated, meaning we didn't really order things very well. But you know, we got it, this final point up here tells us how many peaks were integrated correctly. And so this gets over 80%, and Skyline was getting about 70%, right? So it's not the biggest problem. Like you know, the biggest problem here, actually, because you have to look at all these together. So even with mProfit, we were actually just going up about 5% in the final end thing. But what we did with mProfit was to get a much better calibrated score so that you could tell when it was correct. Okay, so but this was the first plot. What did we think? Well, actually, so we implemented mProfit, and we knew that we hadn't implemented some scores in OpenSWATH. So this is DIA data. This is the OpenSWATH gold standard data set for human, and we knew that we hadn't implemented the Y-series, the isotope correlation, or the isotope overlap scores, because those would require some extra infrastructure, and I wanted to see that they were worth it. So what's your hypothesis at this point, looking at this plot? How is Skyline doing compared to OpenSWATH? Not so good. Oh my gosh! Wow. You guys are way too polite. We were like, okay, we've got a lot of work to do. Okay, so our first guess was like, well, we didn't implement these scores, and our first attempt to answer, is it those scores, is actually on this plot. So who can tell me, was it the scores? You got to read the legend. Was it the scores? So actually, yeah, so it wasn't the scores because we have OpenSWATH 7 scores. So yeah, it got a little bit, OpenSWATH got a little bit worse when we limited it to 7 scores. The blue and the green line, one is Skyline Plus and the other one is Skyline mProfit. So Skyline Plus was our improvement, and so we still have this differentiation. When you import data into Skyline, it will go do its best to peak pick. And this was it doing its best, and this was with a fully trained model. And this was the original score. So anyway, so yeah, 7 scores didn't solve it, so we were like we were perplexed. Until I did some debugging, looked at those plots, actually looked at chromatograms. If you were going to go look at chromatograms, what would you look at to answer that question? Why are they different? What would you look at? Quick way to answer the question of like, okay, wow, I see that OpenSWATH's doing really well and Skyline's doing really poorly. What would I look at? Like these are the kinds of questions that I would like you to be asking. Like, okay, if what I believe, if the hypothesis that wow, OpenSWATH is doing way better than Skyline is true, what else must be true? Knowing that you have a tool as good as Skyline, what else must be true? Nobody, okay. Well, Skyline must certainly be picking some things incorrectly, right? That OpenSWATH is picking correctly, right? I'm looking just for a question, not a guess. Like, how would I tell the difference, right? So we have all the peptides listed. We know what the picks were. Let's go look at the chromatograms for something that Skyline got wrong and OpenSWATH got right, right? That's the obvious way, right? Like, okay, and in fact, and I'm going to show an example. I can't show you an example from this data set, but I'm going to show an example from a later one where we did that. And what I start with is, what is the top scoring thing that OpenSWATH like scores incredibly well and Skyline doesn't get right? And what we found was there's no peak. Like in Skyline's chromatograms had no peak. OpenSWATH is saying there is a beautiful peak right here, and we had no peak. And what it ended up being was an incompatibility between a new SciX WIF reader that we had and our DI isolation scheme. So we were actually, for about a third of the peptides, we were extracting them from the wrong MS-MS scans. So yeah, they had nothing where they were supposed to have beautiful signal. When we fixed that, all of a sudden we were up like this. And we're into the same range as OpenSWATH. In fact, with Skyline nProfit, we end with more peaks picked correctly, and we have we hug the Y slightly less. But then we added some new things, and we were able to come up with something that did as well or better than OpenSWATH on this. But basically, statistically not different. And yeah, we added retention time delta squared. And we already had retention time delta, but we added retention time delta squared. We thought it might be a replacement for retention time delta because of we were thinking about least squares and stuff like that. And we ended up thinking, oh, maybe they work best together. And we still have retention time squared, and I'm going to call into question whether it was a good idea. Okay, so then next experiment, this is the experiment the data that you're using from this multi-center comparison, and this was the first, Pedro Navarro sent around an email and said, okay, I've done it, I've compared all the, he'd been in contact with all of us, I've compared all the tools, and these are my results. And, well, here's Skyline, and this is OpenSWATH and Spectronaut. So what's your hypothesis at this point? What? Yeah, no, but I mean, yeah, maybe. Or maybe just believe me, there were people who wanted to go publish this. This was great news for some people. Skyline is really sucking it up. And we had done enough of these that we're just when we do these curated experiments, we just don't see ever anything that big, like a 50, that's huge. And so I went and did exactly the same question that I just told you. Okay, show me something that one tool got really high score on and Skyline got a crappy score on. And this was it. This was the biggest difference in score. So I just sorted by scores and actually in Excel wrote a delta of scores, and then I sorted by the delta of scores, and I said, okay, what's the biggest delta? And this was it. Skyline had picked this. And the right pick was, do I have that? Yeah, the right pick was there, and Spectronaut did a great job of picking it. But what's the difference? What? PPM? No. Why? What's the difference between why? Yeah, there's lots of interference. Why is there so much interference? Why does Skyline have such a more difficult job to do? I mean, wow, I wish Skyline had picked that, but there's this other thing that's co-alluding with it that, maybe that's it, but it's definitely not part of the picture for Spectronaut. So I went back and I started clicking on points, and this is what I saw, was this is a peak, this is the extraction window. Who thinks that's a good extraction window? It's what? Too large. It's 3 times too large. And at the time, then I looked at it and I was like, well, okay, so you're using 10,000 resolving power, which was the default. And to Pedro's credit, he said, so 10,000 resolving power, which was the default. And I went, okay, thinking well, he ran the instrument, but he didn't run the instrument. Ludovic ran the instrument. And so he was asking me, what settings should I use? And I thought that he had some foreknowledge, and so that resulted in a bad setting. But at that point, Mike and I had thought, well, you want a resolving power, and 30,000 resolving power is probably pretty right for this. You want a resolving power that captures most of the peak. And so this is what, if you said 30,000 resolving power, this is what Skyline would extract for you. And that worked a whole lot better than this. But I decided, hey, while I'm at it, I'm actually going to do some statistical analysis here. And I got up to 60,000 resolving power, and then we started doing centroided data, and I got to 10 plus or minus 10 ppm centroiding, and that's what those look like. And then, because that turned out to be quite useful, we built the ability to do centroided extraction into Skyline. So you'll get to use this. But it didn't used to, the mass analyzers used to be all real mass analyzers, and then we added this centroid and allow you to do ppm. I also added there's this thing called SkylineRunner. If you come to the morning sessions, you'll get to use SkylineRunner. And that allows you to, I was doing all these analyses by hand. I got really tired, and I was like, okay, I just want to go to sleep and let Skyline figure it out. So I added these. These are allowing me to set these parameters dynamically. And this is for, so that was for, this is actually doing M-profit models. And then this allows me to set the parameters like the precursor resolution and the product resolution, and whether I have, and then the retention time width. And then I could just go to sleep and run queries like this, and this would show me how many peptides and how many proteins Skyline had identified. And I could see this is where we started with resolving power. 30,000 was what Mike and I had thought would probably be pretty good, and I decided that, well, you actually between 50, 60,000 was better, and then when I looked at centroiding, it was even better. So, and then I did a retention time analysis where I again ran overnight a whole bunch of runs, and I was kind of surprised that it didn't drop back down here. It kind of just keeps going up. And again, if you come to SkyJams, we'll look at this because we're going to do the exact same analysis on the data sets, running them on your VMs, and we'll kick it off overnight and come back and look at it in the morning. So this was the end result, I guess I'm kind of happy that Skyline's at the top now, but it really, I think that these are not statistically significant. I think we get too caught up in the number. If you come over here, you can see, Skyline ends up a little bit more yellow than some other things. And, DIA-Umpire had 2.18 and 2.14 and 2.26, and I think, well, we're quibbling over very small amounts of precision on the quantitative values. But yeah, so I was, this was pretty good result in the end. So then we also went and did DIA-Umpire validation, because DIA-Umpire came up with a whole bunch of peptides that were not in our library, and so we needed to answer the question are they real? And so I was like, okay, great. I'm going to import the DIA-Umpire results and use them as a library. And hey, I can find the same peaks. They come out with really great scores and they look good. And but Pedro and Stefan said, yeah, but I just might be finding what they told you was there, right? So you might be overtraining. So what they did is the Biognosis guys had a library that had some query coordinates for these 6,800 peptides, and everybody queried those and said, well, can we see them, and do they end up in the same place that DIA-Umpire is saying they are? And it turned out that we really could. And yeah, this will take you a moment to get your head around. Yeah, a Venn diagram with 5 different things, and I guess I'm gonna. Well, can anybody see anything of interest here? I mean, obviously, there's lots of things that we all agree on, and there are not very many things that are, where do we find, uniquely DIA-Umpire 8. So that was good. Is there anybody who's like, hey, why did my tool get this, Okay, I add this circle. What's that circle? Yeah, and who doesn't get those? OpenSWATH, right? And do you see any other tool similarly have a similar scale of missed things? No. So why was OpenSWATH doing suddenly so terrible? So this was my first processing of this data with Skyline, with a plus or minus 5-minute retention time window, which was that was our default for the rest of the data. We had done plus or minus or a 10-minute total retention time window, and these are all the things that Skyline identified. And anybody see anything they're concerned about? What's your analysis? So this is the time from regression. So this is a residuals plot. For the prediction is 0, and then this is how far the peak that was found is from the predicted retention time, and then this is their IRT scores. So as we go out here, we're getting later. These are later eluting ones. These are earlier eluting ones. And what's your question of this data? What would be your next analysis? Does that look fine to everybody? Why doesn't it look fine? Yeah, it's not centered on 0. Yeah, okay. Yeah, let's open up the retention time window. Like, wow, we go right to the edges here, and there's some curvature here. Like, what's going on? Let's just open it up and let Skyline just choose everything wherever it seems to be. Whoa, right? So this is opening it up to 15 minutes. So yeah, that's and these are the questions I want you to be asking, the things I want you to be looking at, and okay, I'm going to do another analysis to try to understand this, right? So it turned out that there was quite a bit of curvature between where the IRTs were from Biognosis so the chromatography between Biognosis and Ludovic was not linear. And that was it. I had already figured this out. This came in, and I said, yeah, are you sure you told them to use a 20-minute window? Because we had agreed, I think at that point, we'd agreed on a 20-minute window. I'll tell that. So we'd agreed on a 20-minute window for Skyline. That's it. And so that was generated like that with a 20-minute window for Skyline. And I said, yeah, I don't think OpenSWATH is using a 20-minute window yet. Turned out that was right. And so then after the fact, we got this, much lower numbers, fixed. And then being as obsessive as I am, I'm like, well, what about these 42 peptides? What? Well, it turns out that the number halves if you go out to a 30-minute window for Skyline. So even those 42 peptides, Spectronaut and Skyline are really doing almost exactly the same. Okay, and so then, we did a huge amount of performance work to get this working because we just had not been working with data sets this big. We did this multi-file parallel importing, which you'll get to do today, later, as soon as I get done. And then I did a lot of analysis of how to make Skyline fast, and I had this, my mantra was, if you pay for computing power, you should be able to use it with Skyline. And what we found was, so we did all this multi-threading, but we found when we got to 24K, 178 gigabytes, really big computers, we could only get our best performance if we went multi-process. So now Skyline command line version has the ability to go multi-process, and you'll get to use that if you come to the SkyJam. But we haven't implemented that in the user interface. So in the user interface, you're sort of limited to this degradation, and you can get almost a 50% speed up. This is a normal dev computer. This is a normal 4-core i7 computer. But yeah, we did a lot of exploration of performance. Okay, more recently, so Bruker came to us and they said, hey, we're getting way higher detections with Spectronaut. And I said, yeah, send it to me. I love these things because there's always something to be learned from them. And so I encourage you, I wonder, it's the shy, I don't want to tell you that plot looks like way better for OpenSWATH than Skyline. Tell me. This is always a good takeoff point for understanding and discovery. So data set 1, Spectronaut got 10,500 precursors. So that's this is a human cell lysate. Kind of similar to the kind of experiment that you got. And then they're like, well, we really improved things in our second data set. There were some problems with our collection in our first data set, and now we're seeing 17,500 peptide precursors detected in Spectronaut and only 14,000 detected in Skyline, 25% more. What's your hypothesis? It's fair to say I don't have one. Tell me what else. Give me some more information. Okay, so then I went and I opened up the mass extraction window and ran these histograms using R. So these are plots from R, not from Skyline, of data set 1 and data set 2, and what do you see? Yeah, wow, the mass error is like at what, 10? And it's got a standard deviation that's quite a bit wider too. So this data set 1, despite the fact that we're actually finding fewer things in it, looks better to us in terms of mass calibration. So, and then I actually went and ran Spectronaut, which was doing fine, and I noticed that, oh, this is data set 1 and data set 2. They have this 2D plot that shows a really nice plot, and yeah, I borrowed from it mercilessly. So this is data set 1. They've got this curvature in data set 1, and wow, crazy curvature in data set 2. And then they have their own internal recalibration. So they just recalibrated, and it didn't impact them that there was this miscalibration. But why are they showing this huge? Well, let's go to, so then I went and did the same plot in Skyline, or not in Skyline, in R. So this is a 2D histogram, and this is what data set 1 looked like to me, and this is what data set 2 looked like to me, and you can see that somehow we flipped our orientation, but it's really just exactly the same plot. We agree, except for we don't agree on data set 1. So anybody have a hypothesis? Well, first, does anybody have a hypothesis? So, yeah, what's going on? Why would I be seeing that as such good and not such good in the other one?
It was already recalibrated.
Recalibrated, right. So this one's been recalibrated. It wasn't recalibrated because I ran Spectronaut, so somehow Spectronaut was not using the calibration information. So Skyline benefits from the calibration information. And when I went into the code in Skyline and turned off the calibration information so that, like, okay, it's there, but we're going to ignore it, then all of a sudden, yeah, now I'm getting exactly the mirror image of what Spectronaut's getting. So for some reason, maybe because they have their own calibration routine, they're not paying attention to the vendor calibration routine. This then, again, I like took me a lot of work to graph this stuff in R. I wanted it to be really easy, wow, another pitfall that people could learn and avoid from. So I made, actually my son came to work for an internship last summer when he's 16, and he implemented this plot. And so this is before recalibration. This is a 1D histogram, and then we now have this in Skyline 2 is the 2D histogram showing exactly the same curvature. And then once I showed this to my collaborators at Bruker, they're like, yeah, we forgot to run this tool. And we run this tool, they sent me back the data, and it looks like this. And then Skyline did much better on that. And yeah, so now Skyline ended up getting 13,800 peptide precursors detected in data set 1. My hypothesis is maybe it has to do with the vendor recalibration. Maybe the diagnosis recalibration doesn't always work as well as the vendor. But it did not turn out that vendor recalibrated data set 2 actually gave me lots better. It gave me comparable detections to Spectronaut, and this is the first number, I kind of stick with that, but at one point I do have an email from the person saying, oh no, I was wrong, it's actually 16,400, so I don't know, somewhere in there that's totally fine. I don't think there's really a statistical difference in how much we're detecting. So then new Bruker, so another data set from Bruker, 12 DDA runs, and we were getting 23,500 on average peptides detected in 6 DIA runs. And then when I put them into this plot, this retention time calibration plot, which you guys have seen, does everybody understand what this plot means now? You feel like, yep, seen a bunch of those. Or are there people that want me to reorient you on this plot? Okay. So what's going on here? Are we happy with that retention time? Yeah, so that means, so these are my IRTs. How far off am I getting? So there's some systematic skew here, and then there are even these like tail distributions coming out here. Doesn't look great, right? So where did these IRTs come from? How did I get these IRTs? Anybody? How did you get your IRTs yesterday? Does anybody know you produced IRTs yesterday? Which tool gave you your IRTs? When you ran those tools yesterday, you're getting IRTs. Anybody? So Spectrast was calculating the IRTs, right? So the library building tool, Spectrast, calculated IRTs for you. And what were they based on? The what? 11 spikes in peptides, but each individual IRT is based on something. So what was the measurement that we said, we know where this peptide comes out? No, but what was the measurement? What was the mass spectrometer giving us that allowed us to say, I know where that peptide shows up? Of retention time of what? DDA what? The DDA runs, but what inside the DDA? Like, okay, I say, okay, here's a peptide. Give me its retention time. What was how did you say? Oh, I know what? Right, the ID, which is the spectrum. So at some point, the instrument measured a spectrum. That spectrum got matched to the peptide, and now we have a whole bunch of spectra, MS spectra, and we looked at a plot, right? We had this plot where we had two IDs on either side of a peak apex, right? So we know that IDs are not as good as having a peak apex, right? A peak apex is really where the thing's coming out. So I was like, well, okay, this looks wonky to me. Let me see if I can correct it by importing the data into Skyline and using the peak apexes as the retention times. Oh, this is how my mProfit model looked on that data. So it was still pretty good. I got, great power in my library intensity dot product, great power in my coelution count. My intensity was okay. Not great for retention time, but I still had a, pretty nice looking model. I did not think, oh, wow, there's something really wrong here, and you wouldn't either. So I had to go look at that retention time plot to say there was something wrong here. I recalibrated using the peak apex times. And this is what happened. And so how do you feel about this? Thumbs up, thumbs down. Hypothesis? Yeah, if I have a 5-minute window. These are things, there's actually, well, yeah, so here's everything's way, within 1 minute of where, the vast majority of things are within 1 minute. I just last night came to a weird understanding of another phenomenon here. We looked at this plot and we said, wow, cool. They're all really close to the right place. But we also said, there's something strange about that plot. What's strange about that plot? Yeah, there's these two lines. Why are the false discoveries lining up at the edges? That's a little weird. And I didn't understand it till actually just last night when the guy working on Trick made an observation that made me go, oh, yeah. So, and this is the model with those IRTs. All of a sudden our retention time becomes by far the strongest. These two sort of work in concert, or we think they work in concert. It was just sort of a guess, and we ran with it. But the weird thing has always been, yeah, Dario reported, wow, it works even better with retention time squared and retention time together, but frequently retention time squared ends up going the wrong direction. And we're like, that's a tuning score, it's probably great, But yeah, so last night I realized, because I had seen one of these before I left, last night I realized, oh, it's retention time squared that's moving everything out here. Because the main model I'm training on says, wow, retention time should be really good, and then somehow this ends up flipped. Now that means that if you somehow escape this center of gravity, now all of a sudden the things that are really far away get dominated by this score. They're like, wow, that's a great peak because it's so far away from the right retention time because it's growing with the square of time. So I'm kind of thinking we're going to remove this, although really it doesn't seem to hurt things that much. But yeah, it's, we're getting to the point where we don't think retention time squared is necessarily a great idea. Okay, so then there was also this other problem. So you know, as I was trying to understand these, you know, what does it mean to be trying to pick an IRT from identification times? Here's one. This is actually one of the IRT peptides. I guess I didn't write which one. But wow, there are multiple, like the fact that there's light blue lines and a blue line here means that for some reason we were identifying it really early and then out at 30 minutes. And then why were we identifying it way out here? Why do we keep identifying it for longer? Why aren't we just identifying everything really close to that peak? Tailing, exactly. Nice. So it turns out that in this chromatography, there were 3 peptides that had this kind of tailing, and that led to us, even when I applied. So first, we were doing our IRTs, you know, back when things looked like this, we were doing our IRTs using the mean retention time, which I decided that's crazy because now this impacts the mean in a big way, you know. So that might cause me, if I didn't have all these things out here, that might cause me to say, oh, I predicted it 20 minutes because that's the mean. But then I switched to the median, but because of tailing, there were some things where if you use the median, they'd end up out, you know, way out here, not anywhere close to the apex. So you can see it can get very tricky trying to pick an IRT retention time from a set of spectra. And I think I've really improved things a lot, but it's by no means a done deal. Okay, so this is tutorial 1. This is the library, and this is the TSV library. This is the library you just generated. These are the IRTs. Who's happy? So what's the problem? I even label this one here. This is so is it all one distribution? No. Does it line up on 0? No. Okay. So and so there's multiple distributions, and the great thing about Skyline is you can just click on these points and it will pop up and show you what is this thing, and after you click on a bunch of these, you'll go, you know, these are mostly yeast, which is actually how I found some of those. You know, I showed you these tails too. Same thing. I just sat there and clicked on these and went, oh, these are mostly from this run. So yeah, these are mostly yeast, and so I think I can promise you, if you come to Sky Jams in the morning, we'll look at how we could correct this. And the IRTs that you can get out of this data are not super great. You can see that they're kind of, you know, there's just no way we can get these IRTs to be this good. That was particularly good chromatography. Is anybody worried that we might be missing some yeast? Why? Yeah, because the distribution actually seems like it goes out, you know, we're limiting to 5 and the distribution looks like it's going out there. So that's one problem. Here's another thing. This is the isolation scheme that you just imported in the tutorial, and that I used through the entire Navarro study. And then I was doing a tutorial, and I added this import button during this because I was just tired of like, oh, send me your isolation scheme. And I'm like, okay, I should be able to just figure it out from the data, right? So this is what it is from the data. It's actually, there's a 0.5 MZ difference. Doesn't make a big difference, but it is, now in Skyline, you don't have to trust somebody to send you their isolation scheme, and they might get it wrong. Okay, so wrapping up here. We've also added these new multi-peptide visualization plots, which I find incredibly useful and informative. We first added this multi-peptide plot, and that was actually an inspiration from Paula Piccati. You know, during a talk she gave during one of these courses, she showed something like this and said, this is what we call the protein fingerprint. And, you know, and she showed like one of the peptides disappeared, and you can say like, oh, we did this and the peptide disappeared. And so I was like, oh, we got to do that plot in Skyline. So now, anytime you select a protein, you get its protein fingerprint, any multiple selection you make, Skyline will show you all the chromatograms like this for its peptides. So you can go Control A, and it will show you the top 100 peptides in your document. This is also showing you the peak areas, and we can see that, this is the multi-peptide. This is the study that we've heard about, the 229 for one site, site 10. And you can see that this is stuff that's all supposed to be consistent. And you can see that even in the IRT peptides, there's some weird variance in the peak areas, just right, at a glance. And then here you can feel happy that your IRTs are all pretty well lining up over the 21 runs. This is from another site, same site thing, and I had run statistics. Again, I had just like run Skyline command line, extracted the values, and started processing with R. And I was like, wow, look at all these great data, these great statistics I can get out of here. And then I finally went and looked in Skyline, and these are just the IRTs again. I went, whoa, what happened here? I did not notice this from the statistics, but it was the very first, I noticed it within a minute of having the document open in Skyline, and it turned out we had a corrupted file, which Ben was able to correct for us. So this is the trick data set that we're going to look at later tomorrow. And in this case, they chose their own IRTs. These are all endogenous peptides. And I was kind of like, wow, look at this log scale. This thing's going like 100-fold, like all over the place. But its retention time is nice and stable, so it is just a retention time standard. So while I wouldn't use it for a quantifier in my proteins, it's the latest eluting peptide, and it seems to be pretty stable. So maybe it's a good choice. But again, these are things, just showing you like all the things you can see. And then finally, these are all the nice people who made this possible. Nick is, huge heavy lifter who's done quite a lot. He did all the document grid stuff and many other things. Don did the nice multi-peptide graphs. He's also responsible for the progress indicator when you import stuff into Skyline that everybody loves. Brian Pratt's been mostly focused on small molecule and ion mobility for us. Max is the intern who's in 3 weeks leaving for Google, but he's been working on integrating Trick, and we hope we're there. That he's the one that pointed out, hey, I think this retention time squared has some weird properties, and led to that aha moment. Vigisha is in charge of Panorama. She got the great, she wrote the first line of code for Panorama, designed the schema. Nat Brace is our guy in charge. He does the webinars and the translation and everything. Kaipo does all the library building, so when you see that Skyline handles 20 different library formats, that's all Kaipo. And Yuval is our junior developer who's done a lot of external tools and things. Lots of collaborators. It's been 9 years. There's a lot of really wonderful people, and I haven't refreshed this slide in nearly recently enough. Also, as I said, these 6 instrument vendors all fund Skyline, and there are individuals at each one of them who give us an incredible amount of their time and expertise, and we couldn't do it without them. That's it.
Right. Terrific. Okay, thanks a lot, Brendan. Is there anything further? Any questions for Brendan at this time, or if not, he's obviously around, and we're going to dive straight into the Skyline tutorial. So I'm going to suggest that we just go straight into this because you need to spend about like 20 minutes setting up the document, but then there's a period where you're going to import the data, and this takes about 20 minutes to do. So you can basically set up the document and do the data import, and then grab a coffee or something while the data is importing. So I'm just going to quickly say a couple of things about what's happening in this tutorial. Okay, cool. So just a few quick remarks to help you get going with the Skyline tutorial. So this is where we are now in this tutorial workflow. I put this picture of the smiley face guy to indicate that we finished tutorial 1. I don't know whether this is really appropriate or not, given the trauma of last night and the command line and running Comet and stuff like this. But so anyway, this one is done, and this is what we're doing next. So we're on to Skyline. So I'm just going to quickly say what we're going to try and achieve here. So there's kind of two main chunks. So the first part is to set up the Skyline document for analysis, and we're gonna do this from scratch. And what we want to do is set up the extraction of the MS2, the fragment ions. We want to set the precursor isolation scheme. We want to add these IRT peptide parameters and set up this IRT calculator. We want to add the target peptide query parameters, right? So from the Spectra library, and we want to add a set of decoys. So this is all setting up. And then the next thing you need to do is go to the DIA data and import it. And this is the time at which you can nip out for a coffee for 20 minutes. And then we're going to look at the peak scoring and FDR control as was described by Ludovic this morning and Isabel in these talks this morning. I encourage you to look. So we've just seen the value from Brendan of looking manually at the data. So I encourage you to try and click through some of the data, look at the XICs, look what the spectra look like underneath, look what the interferences look like, and do this for the targets and the decoys. We can look at the mass accuracy and RT prediction accuracy, which we've just learned is very important. And finally, we want to, second last, we're going to look at this quantitative comparison in this A versus B comparison, right? So these different species mixtures that are in these samples from this LFQ bench data. And finally, maybe take a quick look. Oops, this should say MS1. So compare MS1 versus MS2 data to see if you can notice any difference about this. And so just to remind you, what to watch out for when you're manually inspecting this data. So you saw this slide, I think, from Tina already yesterday, and a version of this from Ludovic as well. So what we're looking for is coelution, peak shape, signal intensity, and these are all the chromatography-based scores, or these are what Ludovic referred to as extrinsic scores, so comparison of the relative fragment ion intensities to the library using this dot product metric. How far away is the peak from the predicted retention time based on this IRT prediction method? And well, we don't have a heavy isotope labeled standard in here, but if you did, you could use this. So these are the kind of chromatography-based scores. Also remember the spectrum-based scores, right? So Brendan told you that you can look at what the spectrum looks like underneath, and you can see where the fragment ions you're looking for are. You can zoom in on these and check whether you're seeing what you expect. Is there a monoisotopic peak? Is the mass accuracy within the expected boundaries? Are there other interferences and this kind of thing? So that's basically it. So just to remind you, the kind of final goal here is this quantitative comparison between samples A and B. So if we're looking at E. coli proteins, there should be a predictable ratio between samples A and B for those, and also yeast and the human should be at equal amounts. And as soon as you see this is the WYSI graphic that Brendan mentioned, then it's coffee time. Okay, so I would suggest you try to get to this in the next 20 or 30 minutes, then take a break, and then we can come back and finish up. So good luck.